Okay, now we've got plenty of time here. So I'm going to show that the complement is, I get to assume that the complement's closed, which means I can have the luxury of writing down assume. Assume that the complement is closed. I'm going to prove that O is open. And I'm going to do it by picking any point in O, and I'm going to find an epsilon ball around it, an epsilon neighborhood around it that's completely also contained within O. But if X is an O, that means that X, this is supposed to be an X, is not in the complement. What do I know about the complement? The complement is closed. What does it mean to be closed? That means it contains its limit points. So if X is not in the complement, X is not a limit point. A limit point of the complement. If it's not, what does it mean to be a limit point? It's a limit point if every epsilon neighborhood intersects this set here with a point other than X. But this is not a limit point, which means that there has to be some epsilon that completely misses this. So there exists an epsilon not bigger than 0 such that the epsilon not around X completely misses the OC. I want to make some sort of a death cab for cutie reference there, but I cannot. And also, I don't know how dated that show is now. You probably know it. Anyway, so here's a brief picture, right? Here's my universe, right? Here I've got O, and out here's the OC. If here's my X, X can't be a limit point of the OC, which means that there can't be, it has to have some space between it and the OC. Which means, once again, I can really just use the same picture. I can draw a little epsilon ball around it that's completely contained within O, because I need to make sure that the points from the OC aren't within the epsilon ball. And if there aren't any points in the OC contained within it, that means it has to be completely contained within O. But that's exactly what I need to prove. This is equal to the empty set. But there are only two options. Either something is in the OC or it's in O. So this has to be completely contained within O. So O is open because if you pick any point X, you will be able to find an epsilon ball that surrounds X that's completely contained within O. That's what it means to be open. So basically the same picture works either way, except here we have a point X, and we're assuming X is a limit point, and then of the OC, and we're trying to get a contradiction here. Here we're letting X be an O, and we know that X is not a limit point, so we get to draw the picture. So the same picture comes up twice, but for different reasons. Here, this is the reality. This leads to a contradiction. So finally, F is closed if and only if FC is open. Well, this just requires some renaming, right? Let F equal, you're right. Let's talk about in terms of open sets, right? OC is closed if and only if O is open, right? It doesn't really matter what you name the set. If you want to call your open set O and your closed set OC, great. If you want to call your closed set F and your open set FC, that's great. It's just a renaming of the same theorem. In both cases, you have something is open if and only if the other thing is closed. So that's just a semantic thing. All right, goodbye.